Looking at the next two we've got congruent chord, congruent arc theorem, and then the congruent chord, congruent arc converse theorem. So these are very nicely named. If you've got congruent chords, then you have congruent arcs. So to look at this one, if two chords of the same circle are congruent, circles are congruent. So that tells us we've got CH congruent to RD. You would have to be told that. Then their corresponding arcs are going to be congruent. So that'll tell us that CH is congruent to RD. So if we put that into symbols, if you start off with CH is equal to RD, and you have to be told that, then you can say that arc CH is going to be equal to arc RD. And this is where the notation comes in real handy, because you got to tell the difference between the chords and the arcs. And then you can have the converse, and converse means opposite. So whereas before we started with congruent chords, so two chords are congruent, with this one we're starting with arcs being congruent. So in this case we have CH is congruent to RD. So if we have a situation where they tell us those two are congruent, then we can say that the chords are congruent. So CH is going to be congruent to RD. So to put that into symbols, if they tell you that CH, arc CH, is equal and congruent to, these can all be congruent, if CH is congruent to arc RD, then you can say that segment or chord CH is equal to chord RD. So to take a look at a couple examples with those. So looking at this one, you got to figure out which one you've got. So looking at this one, I've got a chord right here, congruent to another chord right there. And I know they're congruent because of their tick marks. So I've got chord XY is equal to WZ. So starting with two congruent chords, this is going to be the congruent chord. Congruent arc. So if you've got those two chords being congruent, then you know that arc XY is equal to arc WZ. And they want us to solve for arc XY. Well, XY we don't have a value from, but arc X, or WZ, we have a value of 105. So instead of WZ, we can write in 105. So arc XY is going to be equal to 105 degrees. Looking at the next one, they want us to find arc AC. Well, looking at arc AC, the closest thing that's related to it is segment AC. And because they have a 7 here and a 7 there, I know segment AC is going to be equal to segment CB. And so we started with two chords are congruent. So this is another congruent chord theorem. So if we've got two congruent chords, we know AC, arc AC is going to be equal to arc CB. So that one is equal to this one. Well, they don't give us information on either of those two arcs. We're still able to find AC though, because we know that a whole circle here is equal to 360 degrees. And we know that, I'm going to move this down here. And we know that that part, so AB plus BC plus AC is going to be equal to 360. So arc AC plus arc CB plus arc BA is going to be equal to 360 degrees. So 360 is going to be equal to AC. We don't know how big the value is, so let's make it be X plus CB. Well, don't know that one either, but what we do know is that this arc CB has the same exact value as AC. So that one's going to be X as well, plus BA is 130 degrees. So 360 is going to be equal to 2X plus 130. Subtract the 130 from both sides. And you get 230. Divide both sides by 2. And X is going to be equal to 115. So arc AC and CB are both equal to X. So AC is going to be 115 degrees. Alrighty, looking at the next one. The next one, they tell us that this value here is equal to that value there. And they also tell us that it's also equal to that value there. Let's see what information we need. They want us to solve for X. And the places in the problem where we have X's are on chord AB and on chord CB. Well, chord AB is related to arc AB, and chord BC is related to arc CB. So, looking at the picture, they tell us that arc AB is equal to arc CB. So we've got two congruent arcs. So that's going to be the congruent chord. Congruent arc theorem. Ooh, this is the converse. Because we started with two congruent arcs. So since we know, using the theorem, since we know that the two arcs are congruent, then we can say that their corresponding chords are congruent and equal as well. So we can say that AB is going to be equal to CB. And well, if those two are equal to each other, we can say 4x minus 1 is equal to 3x plus 6. Subtract the 3x from both sides. Leaves us with x minus 1 is equal to 3x plus 6. Nope, subtracted the 3x. So we're just left with 6. Add the 1 to both sides, and x is equal to 7. And I'm double checking to make sure that that's what they really asked us to solve for. So yep, there's our x. Looking at the next one, they want us to find arc MN. So arc MN is right here. There's MN. We know it's equal to QP. We know those two are equal to each other. So, arc MN. They don't give us any information on the segments, but we really don't need it because they've already told us that those two are congruent. Well, we know we need that value. We don't know what it is, so let's represent it with an X. We know about circles. We know that a whole circle, when you add up all the arcs, is going to be equal to 360 degrees. So if we want to try that out, we've got arc MQ plus arc MN plus arc NP plus arc QP. So all four of those arcs together are going to give us 360 degrees for a circle. So MQ is 85 plus MN is the one we don't know that we're solving for, so X, plus NP is 65 plus QP. They don't give us a value for QP, but we know that it is equal to MN because of that tick mark right there. Well, if we've made this one be X, then this one over here has to be x. And they're all going to be equal to 360 degrees. So then we've got 85 plus 65 gives us 150 plus 2x is equal to 360 degrees. Minus 150 from both sides. And that leaves us with 210. Divide both sides by 2. And x is going to be equal to 105. So that means since x is equal to 105, arc MN is equal to 105 as well. Okay, so those are some examples of our congruent chord, congruent arc theorem and its converse. And then looking at the last type of problem that we could do, we've got segments of a chord. So the segments formed on a chord when two chords of a circle intersect. So basically, here's a chord right there. And then here's one segment, and there's a second segment. And it doesn't say anything about them being equal, it just says that's what they are. So from chord HF, we can make segments HG and GF. And then from chord DJ, we made segment DG and GJ. So those were what segments of a chord are. Now with those, they have a segment chord theorem. And what this does is it tells us if two chords of a circle intersect, so in this case we've got FH intersecting DJ, then the products of the lengths of the segments of one chord is equal to the products of the lengths of the segments to the second chord. So the product of the lengths of one chord. So what that's saying is you pick one chord and you've got HG as one part of the segment and you've got GF as the other part of the segment. And it says the products of the lengths of the segment of one chord. The products of the lengths of the segment of one chord, and I'm going to underline them and both the colors for the chord we're using. So HG times, because it says product, GF, so GF and HG is going to be equal to the product of the lengths of the segment of the second chord. So let's do DG times, because it says product lengths of the second chord, and the second part of that chord is GJ. Okay, so if we try that out, we've got two intersecting chords, so we know that that part of the chord times this part of the chord is going to be equal to that part times that part. So 6 times x is equal to 4 times 3. And the big thing is just making sure that the parts that you're multiplying are the parts that make the same chord. So 6 times x, 3 times 4, 6 times, and then from there you just do what the directions tell you to do. This one says find x. So 6x is equal to 12. Divide both sides by 6, and x is going to be equal to 2. So looking at the next one, we've got that first chord. So 6 times x plus 4 is going to be equal to x times 12. And with these, you've got to be very careful and make sure you're using your distributive property correctly. So you're going to have 6x plus 24 is going to be equal to 12x. Subtract the 6x from both sides, and 24 is going to be equal to 6x. Divide both sides by 6, and x is going to be equal to 4. And just double checking to make sure that it really did say find x instead of find this segment. And they could just put more numbers in there to try and make it look a little confusing. It's going to be the same thing. If you've got two chords that are intersecting inside of a circle, it's going to be one segment times the other segment is going to, so one segment is 3 plus 3x is going to be 3 plus 3x times 14 is going to be equal to 12 times 4x plus 1. So 3 times 14 is 42 plus 42x is going to be equal to 12 times 4 is 48x plus 12 minus 42 from both sides. 42 is going to be equal to 6x plus 12. Subtract the 12 from both sides. 6x is going to be equal to 30. Divide both sides by 6, and x is going to be equal to 5. So there's it's really 4 if you count the converses all together. There's the 4 big different theorems that you could have for chords within a circles whenever you're looking at the physical values on the chords and how to solve them. So when you're looking at the segment chord theorem, you're multiplying the two segments of one chord set equal to those two segments multiplied together. So that part plus times that part is going to be equal to that part times that part. And then looking at congruent arcs, congruent chord theorem, if you've got two congruent chords or two congruent arcs, then the opposite is congruent to each other. So if you've got chords, the arcs are going to be congruent, and if you've got arcs, the chords are going to be congruent. And then looking at the equidistant chord theorem and its converse, if you've got two chords that are equal to each other, then they're going to be the same distance away from the center, and then vice versa. If you've got two chords that are equidistant from the center, then the chords are going to be equal to each other. And then looking at the diameter chord theorem, if you've got a diameter with the chord, the two parts of the chord that are bisected are going to be equal, and then the two parts of the arc that are intersected by the chord and the diameter are going to be equal to each other as well. So pretty much, I guess, for this lesson, if you're looking for a short, easy way to do things, if you're really not sure what to do with the values that you're seeing, set them equal to each other. That's not always going to work. Like when you get problems like this, that's not going to work. You're going to have to, with these, you have to look at what you have and work with them. But if you're not sure, set the stuff equal to each other and solve. And probably about 80% for this section, you'll do okay with that. You'll do a lot better if you figure out the names and how they work. But yeah, if you're looking for a short, easy way to do that, for the most part, things are equal to each other. If you have any questions, be sure to write them down on your paper and ask when you get to class.